All right, we have this one last video in this whole parametric equation setup that we'll talk about. We're going to talk about the calculus with parametric equations. And so we're going to do the same basic two things that we've been doing in calculus. We're going to think about derivatives and find slopes of tangent lines. And we're going to think about definite integrals and find areas bounded under curves in the exact same kinds of ways that we're going to do it in our regular X and Y setup. But now we're just going to deal with things parametrically. So let's just get jumping into this stuff. So to start, we'll start with these slopes of tangent lines. Now, notice the slope of a tangent line is still going to be the same kind of visual interpretation. It's still going to be dx over dy because we still want to match it up with rise over run, this delta y over delta x, right? We want to have this kind of like connection in between these two things. Now, these aren't exactly the same because rise over run is like an average rate of change from a point to a point. But when we're thinking about tangent lines, that's going to work out nicely. We want to find the instantaneous slope on our function. So all this to say, we still are looking at dy over dx here. Now, we have functions for x and y. That's like the whole point of parametric stuff. These functions of x and y are based on what the parameter t is doing. So our question is it valuable to know what the rate of change of x is with regard to t and what the rate of change of y is with regard to t? Absolutely that is, right? That tells us a little bit about how we're moving around this curve horizontally and vertically. This might call you back to like related rates problems from Calc 1, where maybe you would find these kinds of derivatives with some sort of a given function of x for y. Now, that's not what we care about in this case, but it is worth it to know those types of things in some cases. What we care about, though, is dy over dx. Let's say that in general, we have a function of x for y, and we have a function of t for x. And we want to know dy over dt. We're going to do a chain rule here, right? dy over dt is dy over dx times dx over dt, where we have this nice little linking stuff here. X is our linking function, or you can say this is like y prime times the derivative of the inside part, which would be x prime for t. That's what the chain rule says. Again, what we care about, though, is this right here. So what we're going to do is just rearrange the chain rule for dy over dx, because in our setup, we have functions x and y of t. So if we rearrange this stuff just by dividing both sides by dx over dt, we get that the derivative of y with regard to x is dy over dt over dx over dt. Or you could think the derivative of the y function over the derivative of the x function here. Now that should kind of make sense intuitively. And it's just a rearranged version of the chain rule, but it's one that we don't talk about as much as like this initial version of the chain rule. All right, the second derivative, how does that work then? This is a little bit mind-bending for a second until we really highlight this part right here. The derivative of y with regard to x is the derivative of that thing with regard to t over dx over dt. That's what we just said. All right, dy over dt over dx over dt. A second derivative is the derivative of dy over dx, though. It's the derivative of the first derivative. So we're just going to put dy over dx in here. All right, so the second derivative is the derivative with regard to t of dy over dx over dt. And again, dy over dx is the derivative of y with regard to t over the derivative of x with regard to t. So everything does work out nicely here. It just takes a little bit to kind of like figure out how this goes. Here's a quick example that we can do. Let's grab the first and second derivative, and then we'll talk about how to interpret that. So dy over dx, we know, is going to be the derivative of y with regard to t. Whoops. So the derivative with regard to t of sine cubed t over the derivative with regard to t of cosine cubed t. We can just do some chain rule on here. We get 3 sine squared t cosine t over 3 cosine squared t times negative sine t. Now we can reduce a whole bunch of stuff, and we end up with, there's a sine left up on the top and a cosine left on the bottom, and the whole thing is negative. We could say, oh, negative tangent t. That's what this thing is. All right, let's think about second derivative then. that is, remember, it's the derivative with regard to t of that derivative divided by the derivative of x. So this is the derivative with regard to t of negative tangent t over the derivative with regard to t of x again, cosine cubed. So this is negative secant squared t over negative 3, cosine squared sine. And again, we can do some simplification. Secant is really 1 over cosine, so this is going to give us some more factors of cosine in the denominator. So this is 1 over 3 cosine to the 4th t sine t. All right, cool. Now, if we want to sketch this thing, hopefully I gave myself another page of this. If not, oh boy, we might be in trouble. We can think about where our function is increasing or decreasing and where it's concave up or concave down, right? We can say, oh, okay, we've got some tangent stuff in between 0 and 2 pi. That means that, maybe I'll draw the tangent function just so we can see it. It's going to look like that. This is negative tangent. That means we start off with a negative derivative. We're going to be decreasing, and then we have a point where our derivative doesn't exist anymore. And that's right at pi, because we've got some asymptotes there, right? And there's our other piece of our tangent function. So this is what the derivative looks like right to there. So that's 0, pi, 2 pi. And if we're just looking between 0 and 2 pi, that means we're going to start with a derivative that's negative. We're going to get really, 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 really negative. That means it's going to be facing down pretty much, and then it's going to have a really positive slope. It's going to flip right away. So that is dy over dx. Or you could say y prime. For y double prime, we've got this thing here. What we'll notice is that this is always positive, cosine to the 4th. So this is only going to change sign based on when sine of t changes sign. So let's just think about sine of t. Looks like that, right? That means we're going to start positive, concave up, and then get concave down. Okay, so we're going to start concave up and decreasing. We're going to lose our concavity as we start decreasing more and more and more. And then at this point, when we switch to increasing, we're going to switch also to concave up. All right, so we can try and plot this thing and see what that really looks like. All right, so let's flip over to Desmos really quickly. And here's our plot of it. And we can see what's going to happen. Now, let's just see. Where did this thing actually start? Okay, so it starts over here, right, at 1, 0. And as we go around, let me put this back to 2 pi. There we go. As we go around, we said we started off with a negative first derivative, right? That means it was going to be decreasing. And that's true. We have a negative first derivative. Now, again, our point is actually going, or our curve is traveling upwards. But if we think about slopes of tangent lines the way that we normally would, we've got a kind of decreasing function here. And then we said we have this impossible vertical slope. That's a sharp corner right there. And remember, our sine function that defined the sine of the concavity was positive. So we have concave up this whole time. That's true. And then we switched to concave down. That's true. We also had switched in there into a positive first derivative, right? So we have this nice increasing stuff, and it all works out pretty nicely there. So hopefully that's helpful to see a little bit of. Just we can use first and second derivative. Oh my goodness, first and second derivative. Sorry, to talk about this kind of thing. I did give myself another page that we could have drawn it. Oh well. All right, definite integrals. Let's talk about how we might integrate things. Oh, I do want to say this. I'll go back, and we can think about where we have horizontal tangent lines and all that kind of stuff, right? Maybe we'll notice that, like, we have horizontal tangent lines when dy over dx is equal to 0. And I notice some people will say this is when the derivative of y is equal to 0, but we'll have to notice that it's really when the whole derivative is equal to 0. So it's when this tangent function is equal to 0. It's when sine of t is equal to 0, really. not just the derivative. Notice if we look at just the derivative of y, we end up with this cosine thing as well, but that gets canceled out. So just be careful about that. Horizontal tangent lines here, vertical tangent lines when the derivative doesn't exist. We could solve for where the slope is equal to 1, right? We could say, where is dy over dx equal to 1? And that's just solving this negative tan t equals 1. And that works out pretty fine that we can do that. We can get when tangent is equal to negative 1, and that's going to be in the second, well, it'll be right here at this point and at this point, right? So this is at 3 pi over 4 and all that kind of stuff. So that's something that we can kind of mess around with and see. All right, now I want to move on to definite integrals. All right, so for definite integrals, this is a little bit tricky to think of. Let's say we've got this parametric setup that we have, and we're going to have an interval of t values from, we'll call it c to d. I don't want to call it a to b because that's normally what we define our x values as when we write definite integrals. Notice that normally we write a function y of x here. What we're going to notice, though, is that since t is f inverse of x, by just inverting this thing, that means y is g of f inverse. And so if we write that here, then this is really the integral that we're trying to deal with. The whole point of that is that now we can use a substitution here, right? We can set up a substitution where x is equal to f of t, just like it was defined in our parametric setup, and that means that dx is f prime of t dt. That means we can say that becomes f of t, and that becomes now g of f inverse of f of t. That's going to be g of t. And then dx becomes f prime of t dt. And I'll underline this. We'll also notice that we translate our limits of integration from x equals a and x equals b to the new corresponding t values. But we have to maybe rearrange things depending on like what values are going to come first. So normally we'll have like a from t equals c up to t equals d, right? And it's not necessarily true that whatever A was is going to correspond with what C was. So we'll just make sure that we keep the direction that we're traveling here in mind. I'll show you what I mean when we do this example. So we're going to find the area bounded by this parametric curve. Remember, this is the one that we messed around with in our last video. It was the one that ended up kind of bouncing like that. So we're going to try and find this nice area here. So what we'll see is that this is f of t, and we'll call this thing here g of t. We have our nice values of t to start with. So we'll say, all right, this is going to be an integral from 0 up to 6 pi of, we can go back to this formula, it's g of t times f prime t dt. So this is going to be 1 minus cosine t times the derivative of x. So this is going to be 1 minus cosine t dt. And now we end up with an integral from 0 to 6 pi of 1 minus cosine t squared dt, or if you want, you can write this from 0 to 6 pi of 1 minus 2 cosine t plus cosine squared t dt. And this is something that we could integrate. We might have to use a little double angle formula or half angle formula, whatever you call it, on this term, or you could do integration by parts or something like that. If you wanted on there, that's fine. We know the antiderivatives of all the other stuff. We can just use the regular old fundamental theorem of calculus on this. So I'll let you finish that one out to see how we might do that. But that's how this goes. So we really are just using a quick little u substitution on this thing.